Ok, très bien. Alors, on va commencer. Alors, bienvenue à cette réunion du Paris Machine Learning. Donc, il s'agit du 9e Paris Machine Learning de cette saison, la 9e, voilà, en l'occurrence. Aujourd'hui, nous recevons Slim Frikha. Alors, Slim est Data Scientist Senior à Contentsquare. Slim va nous parler de... Alors, le titre de son intervention est Web Page Tree Node Classification with Deep Learning. Donc, Slim va nous parler, donc, vous l'avez bien compris, de classification, mais de classification de zones d'intérêt au sein d'une web page. Voilà. Et tout cela grâce à des techniques de machine learning et spécifiquement de deep learning. Alors, je ne vais pas prendre plus de temps. Je vais laisser la parole à Slim, qui va à peu près s'entretenir avec nous durant, on va dire, grosso modo, on va dire 45 minutes. Et ensuite, on n'oubliera pas, bien entendu, à l'issue de la présentation de Slim, cette présentation d'ailleurs qui sera faite en anglais, à l'issue de la présentation, on posera toutes les questions techniques nécessaires. Voilà. Donc, Slim, je te donne la parole, c'est à toi.
Thanks, Frank. So hello, everyone. In this talk, we'll be talking about web page tree node classification using deep learning. So this is a patent pending solution that we've been working on at Contentsquare for some time now. And so in this talk, we'll deep dive into how we can apply deep learning on a tree data structure using this solution as an example. So I'm Slim. I'm a senior applied machine learning engineer at Contentsquare. I've been here since 4 years now, and I've been mainly working on semantic understanding of websites and web pages. So some words about Contentsquare before explaining and digging into the problem and the solution. So Contentsquare is an experience analytics platform. Basically, what we do is that we're going to install a JavaScript tag on the client website so that we can capture every interaction and gesture of the website users. And then we'll actually use that data in order to build metrics and KPIs and visualizations for the client. So for example, it can be the loading time of the page, the time spent on a specific page, the click rate for a specific zone, for example. And then we'll actually use those KPIs in order to give recommendations for the client in order to improve the UX of his website. So let's start by stating the problem that we want to solve today. So in order to understand the problem, we need actually to understand what's a zoning and why do we need one. So zoning is actually a Contentsquare concept that we use in the Contentsquare platform. So basically in a web page, some zones are more important than others because they're going to have a business meaning. So for example, you can take the search bar, the menu, the product picture, the add to cart button, etc., etc., etc. And so we want, because they are important and they have meaning, we want to basically monitor and analyze these zones. So zoning is basically a set of flagged zones on a given web page. Each zone will have a name that we can see here and a type. Like for example, it can be search bar, product picture, add to cart button, account redirection, cart redirection, etc., etc., etc. So on the screenshot that we have on the right here, we can see that we flagged several zones. We have the list of zone names here, and for each zone that we select, they're going to have a colored overlay. And in this example, what we do is that we display as a example of application, the click rate of each selected zone in the page. Why do we actually need the zoning? It's that because whenever we want to leverage any automatic analysis that needs the page content context, basically we need a zoning. So if you take an example, I want to compare the search bar performance over different page categories: home, products, cart, checkout page, etc. So on all of these pages, if I want basically to compare the performance of the search bar, I need the search bar to be flagged on all of these pages in order to be able to do the comparison. And so that's why we need to create these objects. So how do we create zoning? So basically we select or choose the web page on which we want to create zoning. And then we can select zones one by one, and each zone will actually have a colored overlay, and we will have the list of zones on the right. Knowing that we flag in average 30 zones, which takes 15 minutes, and knowing that we do that for at least 10 different page categories, this step of configurations take around 2.5 hours in order to have a comprehensive configuration of zonings. And so you kind of understand where I'm going. This is too manual, it's cumbersome, time consuming, and there is this human bottleneck for any feature that depends on the zoning. So today, if we want to leverage the zoning data, we need for someone to actually create a zoning before starting and using that data. And so naturally, we want to automate all of this. And so the problem of today is the following. So for a given web page, I want to spot and classify interesting zones. Before going into details about the solution, we need to first understand the data and see what's available for us in order to solve this problem. For those of you who actually didn't do any web dev, let's say, before, and in order to understand the data set, we need to first understand how a web page is represented. So a web page, or what we call a DOM tree for document object model, is basically HTML code that we write on the left here. It's mainly comprised of tags. And the way we write HTML code is that we define zones inside zones inside zones inside zones. So if I take a simple example, for a given web page, I'm going to create a header zone, a zone that is in between, and then you have the footer zone. And then in the header zone, I'm going to say, okay, I have maybe among others a menu, and then inside the menu, I'm going to have a sub menu, and then inside the sub menu, I'm going to have a text, for example. And so this logic of defining in the HTML code stuff inside the stuff can be actually seen as a tree, and that's why it's called DOM tree. So what we need to keep in mind is that web page from HTML point of view can actually be seen as a tree data structure. And because of the way we define HTML code and as a tree, multiple nodes in that tree can actually point to the same zone. So if we take the example on the right, here we have the menu example. And we have 3 nodes in the tree of the page that will actually point to the same zone. So we have the yellow one, the blue one, and the red one. The yellow and blue have exactly the same coordinates. The red will actually have only the same coordinates on the horizontal part. And in the HTML code, we can actually define yellow. Inside it, there is only the blue, and inside it, there is only the red. And so all of them, they point to the menu. So what we did for the annotations when we actually select the zones in the zoning is that we said, okay, so we're going to basically select the biggest zone that comprises only the target zone only. So in this case, for the menu, it's going to be the yellow one. If I go maybe up in the tree to select a more bigger zone, maybe I will actually include additional information other than the menu, and then it's not going to be right. So keep in mind this example of the yellow, blue, red zones, because I will actually make reference to it in the next slides. And so the dataset is the following. So the dataset is comprised of 3 stuff. So first we have naturally the web page. It can be seen as a screenshot image of the web page or the HTML code of the page. We will have the web page categories, so home, product, cart, checkout, confirmation page, etc., etc. This data is actually already available for us in the Contentsquare platform. And then we have the set of zone annotations, and basically it's the it's a pair of the zone X path and the zone type. So if you take this example here, you have the zone type, chat, search bar, product, picture, etc., and then we have the X path, which is basically the root, the path, sorry, from the root to the of the tree of the page till the node itself. And to make it even more simple, it's just a way to have a unique identifier to be able to identify the zone in the page. The dataset is comprised of 400 web pages that comes from 200 different websites. And for the labels or the zone types, basically what we have is that, so we have different page categories. And so for each page category, we're going to have a fixed list of zone types. So for example, the homepage, maybe I'm going to have 8 different zone types. In the product, I'm going to have maybe 15 zone types. Depends on what I want to actually, spot as interesting in each, page category. And so the current scope is, and this is actually the scope that I am going to use to present the following slides, is comprised of 5 different page categories with 29 distinct zone types. It doesn't mean that this is actually the final scope, because I already said that we have at least 10 different page categories. So this scope is going to evolve in the future to have more page categories, and also for each page category, maybe have more zones to detect. And also in the future, if we want to follow the new trends of the web dev, maybe we will detect, we want to detect new zone types. And so if you want to do that, we need to constantly maintain this list of zones that we want to detect. So you can see actually this scope of list of page categories and zone types as a quicksand. It will be constantly moving, and so we need to actually find a way to address that.
Ah, ils enregistrent, c'est chouette.
Okay, so now we can go to the solutions. So for the, actually we tried several solutions. We won't be, we actually will be listing some of them here as some possibilities, but I will only explain at the end the final solution and only the final solution. So the first question is going to be, what are going to be the features that I want to use to solve this problem? And the first option is to say, I'm going to do feature engineering. The pros of this solution is that, of this option, is that it's going to actually be low complexity system with very interpretable, features. But the cons are going to be the fact that the feature engineering is very label dependent. So for example, in our case, we tried first to have a classification that only classifies 5 different zone types. And then when we wanted to scale to 30 zone types, it was way more difficult. We needed to actually try to craft features from a business point of view that would actually be able to address all of those zone types. And so we actually thought that feature exploration would take time, and if actually the list of zone type is going to be changing over time, it means that each time there is some change, we may need to do feature engineering again, and so this may be not optimal. And also, depending on the features that we're going to craft, one of the problems could be the fact that the problem complexity would be way higher than the solution complexity. The fact that the feature that we will craft will basically summarize a lot the information that we already have in raw, and won't be able to be used for a model or a rule-based system in order to answer the problem in a good way. The second option is to say, I'm going to use computer vision on the web page. So the pros is that we leverage computer vision famous backbone models, so VGG, ResNet, or anything else. We will use any object detection or semantic segmentation model like YOLO or wherever. We won't have the need to craft our own model. We'll actually take this model and apply it with some very basic fine tunings to have results. and there won't be any label analysis dependencies. So here in this case, the model will actually learn the features that he needs to learn directly from the raw data in order to address and answer the question or do the prediction in a good way. For the cons of this option, I think that the rendering cost is the one that is the more important one. So imagine that you train this model, and now you have a computer vision model that you want to use in inference. Each time that you want to have the zone types for a given page, you basically need to render the page first, to take the screenshot on that page, and then to use that image to feed your model to have the prediction. And the rendering part is basically costly from an engineering point of view, and so it's actually not, it's going to be a blocker, you know. Also, the object detection or semantic segmentation model will have unnecessary, algorithm complexity because of the fact that we already know what are our nodes and where they are and what are their coordinates. The object detection, for example, would actually look for the zones, look for the objects or the zones in our case, will predict their coordinates, but we already have them. So it's actually useless to do that. And finally, because of the fact it's going to be a deep learning model, naturally, like this model would be harder to interpret compared, for example, to the first option. The third option is to apply NLP on HTML code. So the pros of this solution is the fact that you don't have any label analysis dependency. So the model will craft his own features to answer the problem, and there won't be any rendering needed. So for a given web page, using a simple get, you can actually get the HTML code of the page, and then you apply on it the model, and you get the answer afterwards. For the cons, so because this is highly going to be a deep learning model, there will actually be higher complexity and harder interpretability. But also, we will need to craft our own model from scratch, because there won't be any model that's like on the top of the shelf that will actually take and apply directly to answer the problem. And so what we did is that we selected the right option, which is basically do NLP on HTML code. And then we started asking this question of what task are we going to train the model on to learn how to spot the zones. And so the first one was to say, I'm going to do a zone by zone classification, meaning that for a given web page, I'm going to have all the zones and give them to the model one by one in order to do the zone type classification of each zone. And so for the pros, this is going to be easier to model and train, because you can actually extract each zone alone and then pass it to the model. But for the cons, the training annotation first will be partially different from the user annotation. So recall the example of the menu with 3 nodes that are yellow, blue, and red. So the user actually will be annotating the yellow zone. But for our training, because the model doesn't know all about the page, he only sees the zone itself, we need to also make the blue and red zones as menus as well, which is not what the user annotated. The second con is the fact that we don't have any access to neighboring information. So here in this case, because we only give the zone, we don't see what's happening around the zone. And so sometimes it's useful. And the last one is that we'll actually need to decide which HTML code snippet to use. So is it going to be the HTML code snippet of the zone only? Do we include or not the children HTML code snippet or not? Because sometimes it can have valuable information that can lead to do the right classification, etc., etc. The second option is to say I'm going to do simultaneous page zone classification. So it means that the model won't take zones one by one, but basically it would take pages, and for each page, we're going to classify each node in the page or DOM tree or zone, each zone into a zone type. You can see this as in an analogy, like when you actually do the task of semantic segmentation, you have an image, and then for a whole image, you will classify each pixel in the image into a a label or a class, it's the same thing, but applied to kind of a tree structure. For the pros, so because we actually give the whole page, it's possible to access for a given zone the children and parent information. You just need to use the proper tools. And because also of the fact that it's possible now to access the children and parent information, we know that for the zone, for a given zone, we'll actually use the HTML code of the zone only without any children. And then if you want to access the children information, I'm going to actually use some recursivity or whatever in order to be able to access that information. And also the training annotations are going to be exactly the user annotations, so we don't need to change any of that. For the cons, this model will be harder to train because of page batching. So we said that the model takes pages as input, so our samples are going to be pages. And so a batch of samples is going to be a batch of pages. And so because of the second point, which is dynamic graph complexity, is going to be hard to batch pages. And so the second problem, which is dynamic graph complexity, is the fact that in a given page, the number of nodes or zones are going to be variable. And so when there is variability, it means that in classical, I would say, deep learning techniques, maybe we'll actually crop or we're going to pad, but this is not possible in our page because it will actually result into maybe deleting some information of the page. So we can't actually have that, and that's why we need to have a model that is going to be a dynamic graph. Also, because of the fact that we're actually accessing children and parents by recursivity, it means that there will be possible problem of vanishing gradient. And so the final solution that we took was to do NLP on HTML code and to have a page as an input. So this is the final solution that we're presenting today. So the model takes a page as an input, and it will actually classify each node in the page, which is a DOM tree, into a zone type. So the page is a DOM tree, which is the combination of the HTML code and the tree structure. And then as an output, each node will actually have a zone type. Notice that some of those zones have the label or zone type equal others. So why? Basically, what's this zone type? So in the annotation time, when the user will actually be selecting a zones of interest, imagine that the user is on a page that has 2,000 nodes or zones. He will select maybe 30 interesting zones, and all of the others, because he can't actually select all of them, all of those that weren't selected by the user will be automatically assigned to the class others. You can actually see this maybe as a kind of a trash, class. Okay, so now let's go deeper into the model. So we give a page as an input. For each node in the page, we'll have features that we'll explain in the following slide. These features will actually transform them for each node into a representation vector. And then what we do is that we'll actually combine those representation vector of nodes with the tree structure in order to build for each node a context vector. This context vector will basically, its job is to basically see what's happening in my parents, so around the zone, what's happening in the children, so inside the zone, to have a proper context vector. And then we'll combine the context vector and the local node representation vector in order to have the node vector that we will use to do, that we'll actually use in the decision block to have the node types at the end. So in the following slides, we're going to have more details about each of these blocks to have a clearer view. So first, let's start by the inputs. So the first input is going to be the features for each node. So what we do is that we take the zone HTML code snippet or the node HTML code snippet. We're going to delete from it the all the children HTML code snippets. And then from this resulting HTML code, we will actually extract several information. So the first thing is going to be the displayed text as the user see it, in the rendered version of the website. Then you're also going to extract the HTML code input. So without the text that is here, we will also extract two important attributes, which are the ID and the class name, because frequently these two attributes have some valuable information in them. And then we're also going to extract additional other attributes. So it's actually 10 other attributes like role, type, name, etc., etc. But we group them into one feature. So the thing is that here, if we take those 10 attributes and we want them to, model each one of them as a separate feature, sorry. The thing is that these attributes are actually very often empty. And so it means that if we model them each one apart, it will we will have basically very sparse inputs. And so we decided, instead of modeling them each one apart, to group them into one feature, which is the other attributes, by concatenating them with a special pipe, with a special character, which is the pipe. The second model input is going to be the tree structure. So what we do is that we take our tree, we assign an index to each node, and then we just compute the adjacency matrix, which is the parent-child relationship. So here, for example, A and B, A is the parent of B, so 0 is the parent of 1, and then we have the 0, 1 relation, which is this edge, etc., etc., etc. Okay, so now let's move on to the next block, which is the node to vector block. So this block takes for each node all those 5 features that I just explained, and then he will compute one representation vector for each node. So for all of these features, so for each node, they are basically modeled as a sequence. It's text, so code, and so it's basically a sequence. For the display text is going to be a sequence of words, and so we'll use BERT as an embedding for the words in this sequence. And for all the others, we're going to actually see them as a sequence of characters. And so for each one of them, we will have an embedding layer at the beginning to learn the characters embedding. Each one of them will basically output a vector of representation of that feature type. And then we'll basically combine those 5 by concatenation and then apply dense layer to have the final vector of representation for each node. And so now let's move on. Let's dig even deeper and understand what's happening inside these 5 blocks. So it's the same block. Basically, we take the sequence input as the sequence data as input. It's a 2D matrix where the rows is basically the sequence length and the columns are going to be the embedding size. And then what we're going to do is that we're going to stack 1D convolutions with global max pooling 1D to have a vector of representation at the end. But we're going to do that with multi-branching, where each branch is going to have a different filtered size for the convolutions. Why you do that? So that the model can basically see closer or wider in the sequence. And so afterwards, each block will basically have a representation vector at the end that will concatenate and apply a dense vector, a dense layer, sorry, to have the vector of features at the end. So now let's move on to the context to vector block. So the context to vector block now takes as an input the representation vector of each node and the tree structure. And he will use those in order to craft the context node features for each node. So in order to understand the context to vector, we need to understand this layer, which is the tree LSTM. So tree LSTM is basically the generalization of famous LSTMs to tree structured data. So it's the generalization from 1D sequence to ND sequences. And it's a paper that was out in 2015. And that was used in the paper to model a sentence as a tree in order to build a sentence embedding vector for a given sentence. In our case, we'll actually apply it to access the information of parents and children in the tree. And the way it works is that basically before, for the 1D LSTM recursivity, what we do is that for given state or step in the sequence, what we do is that we compute the current hidden state using the current input and the previous hidden state of the previous hidden state. This is the 1D sequence. And for the n-dimensional sequence, what we do is that we compute the current hidden state using the current input and the sum of hidden states of the children. This is actually what is shown here. And also for the memory, it's the same thing. So it's going to be a weighted sum of the memory cells of the children to be able to have the memory cell of the current step. So how are we going to apply this tree LSTM in our case? So what we do is that we chain bidirectional tree LSTMs. So the input is that we have a tree structure. For each node, we have a representation vector. What we do is that we apply a first tree LSTM in an upward recursion fashion. So it means that for each node, I'm going to compute its hidden state using the sum, using the input of the node itself, which is the local node vector, and the sum of hidden states of its children. That way, basically, we'll inject the information of the children inside the node itself. And because its recursivity for B is going to be the same thing, so basically we will be injecting inside A all the information about what's happening under A. And so this is the first step. And then what we do is that we have a second step where we basically flip the tree upside down to basically be able to do a downward recursion. So for the downward recursion, what we do is that we inject back the information of A into B and C and G, but the input of the tree LSTM of the second step, which is this one, is not going to be the local nodes features, but are going to be the hidden states of all the nodes in the step one recursion. Why we do that? So basically, when we do the upward recursion, we inject the information of the children inside the node itself. And if we use the same vector to propagate back to the children, because A here, hidden state of A in the step one has information in B and C and G, when we propagate it back in B, we will see A, but we also see C and D. So in the node, I'm going to be able to see my parents, I'm going to be able to see my siblings, and I'm going to also be able to see the children, my children. And because basically this is very complicated graph, we will have for sure vanishing gradient problems. And so in order to address that and improve the flow in the graph, what we're going to do is that we're going to introduce residual connections. So at two stages. So the first one is that for the memory cell downward of a given node A in the step two, what we're going to do is that we're going to sum the memory upward of A plus the recursion formula of the memory of A in the step two. And for the hidden state of each node here is going to be the sum of the hidden state resulting of each node in the step one and the hidden state of that node or that same node in the downward recursion two. And so at the end, the context vector of each node is going to be the hidden state of A, which is the sum of these two. Now let's move on to the last block, which is the decision block. So the decision block takes the features of the node as an input, which is basically the combination or concatenation of the context node feature and the local node features, and will actually have node types for each node in the tree. So what we do is that we're going to do n classification at the same time, n being the number of page categories. So for each head here, each output head is basically the classification according to one page category. And so at the end, and so each block here is going to be usually, stacked dense layers with softmax at the end, and we're going to use the web page category, which we have as an input, in order to select the right head at the output and use it as our final classification for all the nodes. One question could be, why do we actually have one model for all the end page categories instead of having one model per page category? So the first explanation, which is obvious, is the fact that training, maintaining, and serving and maintaining one model is way simpler than having n models that you need to train, serve, and maintain. But also, this is the most important reason, is that we want the page categories to benefit from each other. So remember that we have zone types that can actually occur in all the page categories or in some of the page categories. For example, the menu zone category can actually be present in 2, 3, 4, all the page categories. And so if we train them simultaneously in this multitasking fashion, the menus from all the page categories will actually benefit from each other. And then instead of basically separating, data per page category, and you will have basically a training for a menu of a given page category only. And so that's it. So the model summary is all of it in here. So we give for each node in the page all the different features that we basically transform into one representation local vector that we combine with the tree structure in order to have a context vector for each node at the end of this block. We combine that context vector with the local node vector in order to do the decision on each page category, and then using the right page category input, we can actually select the right output and have the right classification at the end. Okay, now let's move on to the training and results. First, some training tips. So first, we have a very specific data split problem here. So given the fact that websites are going to be built around repeating the same templates, so for example, in the same website, we'll actually have the same header everywhere. We can't actually have two pages from the same website not being in the same data split. So one page in train and one page in validation from the same website would basically give us a data leak problem, and we don't want that. And so for the data split to be bulletproof, we need to actually make him meet several constraints. So the first constraint is the fact that we want the split to be done on domain names or websites. So some website will be only in training, others will only be in validation. But also we want the classical data split constraints to be met. So if I want to a 80-20 data split in my data set, I need to basically have an 80-20 split from a samples point of view with an error threshold criteria, of course. And I want also by class to have the same 80-20 split to also be respected. Otherwise, it means that the split that we did on domain names is not basically representative of the dataset itself. The second tip is doing a custom loss. So first, we have a high data imbalance. So remember that I said the example of earlier, I said in a web page, you have 2,000 nodes. We will select in them maybe 30 zones as interesting zones. And so 1,970 zones are going to be in others. And so this is basically high data imbalance that we want to address. And so what we do is that we're going to use the focal loss. It was introduced in one paper. I don't recall which one exactly. I think in object detection. And so basically what it does is that focal loss shifts the paradigm of loss computation from a fixed weight penalization in the cross entropy. So fixed weight meaning for each class you have one given weight per class, to a dynamic one by using the predictions of each sample itself in order to penalize the sample in the loss. Also, we have another problem, which is the multi-head output. So I said we have n classifications at the end. So what we do is that we want basically to only account for the right page category loss and ignore all the others in the computation of the loss. So what we do is that the training we give a masking vector in order to mask all the other page categories and only leave the loss of the right page category. And finally, what we do is that we use a custom macro metric. So the metrics that we want to monitor are the precision, recall, and F.5 score. Why the F.5 score is because we want to give more importance to the precision. And why we want to do that is that because we prefer that the model doesn't spot interesting zones, then rather than to spot zones and highlight them, and those zones weren't actually supposed to be spotted. So what we do is that for each page category, we compute the metric on each class. So for example, the precision on class 1, 2, 3, and 4 and others. We exclude the others class from that list, and then we apply the mean to have the macro precision on that page category, and then we apply the mean over all the page categories to have the macro metric kind of way. So that's it, and now we have the results. So we have a custom macro F.5 score of 76% on the validation versus 96% in the training. Something that I omitted and didn't actually say is that we apply, of course, dropout and batch normalization to actually prevent the model from overfitting. We have a macro precision of 83%, which is good because we favor the precision over the recall. And what we notice is that we have variable performance over those 29 classes that we have in the current scope. So here we have some examples of the current of the top F.5 scores, but we can even have some classes that can drop to maybe 20%, and the performance, the class performance is actually highly correlated to the number of classes. So if you have one zone type that is present in 5 page categories with high presence, it's easier to learn it than to have one zone type that is present only in 1 page category, and it's even rare in that page category. So then what we did is that, so we take this model, we thought that this model is pretty good, and so we took it and we basically wrapped it into a Chrome extension. The goal is to basically apply it on live web pages to see what it does on live web pages. So we just select the page category, and then we launch the model to have the results. Very important, this example of screenshot Ubaldi is basically not part of the training because otherwise it's too easy, and so when you apply the model on the website, you can see that it detects several interesting zone types here. And so for each zone type, when you actually hover on it, you can have the classification confidence of each zone. Something that we need also to highlight is the fact that after the model inference, we have a post-processing step where we actually select one zone for each prediction of pool of zones. So if we take back the same example that I already gave you earlier about the yellow, blue, and red zones being all the same menu, in the model today, we don't have any modeling that would actually enforce that we have one prediction only for that pool of zones. And so what we do is that we basically select only one of those zones and basically say that this zone is going to be the zone that I'm going to highlight. Okay, we're approaching the end, so let's conclude and wrap up. So we succeeded as a conclusion to build a generic model to learn zone types on web pages. So for me, A and B are the most important characteristics characteristics of this model. One, there is no, this model is basically agnostic of the list of zone types. Remember, the zone types and page categories scope is seen as a quicksand. So there is no feature engineering. You give the HTML code raw features and you let the model learn the features that he needs himself. And it's basically agnostic of the list of page categories. So if the list of page categories changes in your data set, the architecture of the model at the end will actually adapt and add or delete, additional heads in your training. And we succeeded to build this model with a decent performance only on 400 pages, which is something good. So now, if you want to train this model on a new data set, we will actually update the scope of labels, zone types, and page categories. It would be actually effortless. We just need to have the right data set with the right annotations, and we'll actually launch, training on it again. And so for the next steps, what we're going to do is that we're going to scale the data set to improve the performance drastically. So we believe that if there is no point of complexifying the model using, more, I would say, complex modeling in order to improve the performance, I think that we hit a ceiling glass, because we only are using 400 web pages, which is basically 300 roughly in the training and the rest in the validation. And so if you want to improve the performance, it's better to go and get way more data than to basically complexify the model. We will also scale the list of zones and to more zones and to more page categories to actually be able to apply it on all the page categories with more zones. And we will also serve and leverage this solution progressively to be able to use it in the product, in the Contentsquare product. That's it for me. Thanks for your attention. And I guess it's now time for questions.
Alors, je te remercie, Slim. C'était tout à fait intéressant. Alors, il n'y a pas eu vraiment trop de questions dans le chat. C'était essentiellement des références bibliographiques qui ont été échangées, étant donné que ton exposé était tout à fait détaillé, hein, en ce qui concerne les points techniques qui pourraient être litigieux en quelque sorte. Voilà. Alors, néanmoins, moi, en ce qui me concerne, j'ai noté quelques questions. En ce qui concerne l'implémentation, un peu dans le désordre, hein, j'ai noté un peu comme ça me venait. En ce qui concerne l'implémentation, vous avez utilisé quel framework chez vous pour le faire? Keras, TensorFlow, PyTorch?
Je vais répondre en anglais, comme ça, en fait, je reste en
Ah
fait,
oui, pardon, oui, ok.
Tu peux poser en français, mais il n'y a pas de souci, moi je réponds en anglais, comme ça, en fait, on reste.
Très bien.
So the question was, what framework did we use to implement this model? The answer is we used PyTorch. The reason why behind that is that we think that PyTorch, we think that PyTorch is way more, Pythonic in the way you write the code than, for example, TensorFlow or Keras. But the second and the big reason is the fact that with PyTorch, handling dynamic graphs is, I think, way more easier to handle than using, Keras or TensorFlow. Maybe it changed over time, but at the time of basically implementing it was the obvious reason for us. And also because of the fact that we, tree LSTMs basically are a dynamic graph, so we needed to have a proper implementation to basically have it and use it and like maybe do some changes in it. And we find a very suitable implementation that was done in PyTorch. So for us, even though there was also other implementations in other language, in other packages, but the one that was actually done in PyTorch stood up, and so that's why we use the PyTorch.
Okay, no more question in the chat. So, okay, I have another question about the computing time. How fast to compute, to classify a web page in production?
So basically, this model didn't hit really production for the moment, because the current performance needs to be a little bit improved to basically like make it go to production. So that's why we said we want to have more data sets, more pages in order to to improve drastically the performance. But we actually did some profilings in order to know if actually this is going to be like a major blocker or not for us. What we did is that we did several tests using SageMaker, and basically because one thing that we need to account for is the fact that the page is a dynamic graph, and the dynamic graph size is going to be function of the number of the nodes in the page. And so the more the nodes you have in the page, the more the inference time would be higher. And so for a page of, let's say, 1.5K or 2K nodes using a GPU in inference, it takes something around 1.5 seconds to do the inference of all the the final prediction for the whole page. If it's on CPU, it takes a lot of time, which is basically kind of something that we would wait for, because of the fact that the graph, can be very long, and so you need basically to find a solution to make it faster.
Okay, so Franca asked you, for node feature embeddings, did you use pre-trained models? Did you fine-tune them?
So for the nodes embeddings models, what we did was basically to say that, let me see back. So for the inputs, are the inputs, and then for how we actually embed them, what we do is that for the text, we use pre-trained embedding, which are BERT, because basically we model them as a sequence of words. So we don't basically want, if there is something that is available that we can use, we don't basically want to reinvent the wheel and build our own embedding. It doesn't make sense. But for all of these inputs, we said that it's a sequence of characters, and we have our own embedding. And basically, if you said that the vocabulary of characters is going to be comprised of the printable characters, which is basically 100 characters, then you will actually embed those 100 characters in a very small embedding space, and use that as an input in this block. One of the questions could be, why don't we basically do word embeddings in this in all of these inputs? And the answer to that is the fact that this is HTML code, so it's not like natural language where that words are separated by spaces, and you can very easily do tokenizations to have tokens which are words. In this case, if you want to actually do word tokenization, because it's code, if I actually come back maybe to this thing, you don't know, do you actually compute this as one token, or do you actually see it as two tokens separated by this? And some people would actually use other special characters to separate some words between each other. Sometimes it's actually not separated at all. It's going to be for example, in this case, menu bar without any special character in between, and then you can actually compute the right token. And so it means that if you want to go with word tokenization techniques on this kind of code, you won't actually be computing very qualitative tokens, I would say. And even though you would use afterwards a pre-trained embedding, or you do your own embedding, you won't actually be finding a qualitative result.
Alors, je ne vois pas d'autres questions dans le chat. Alors, j'avais une dernière question. En ce qui concerne la taille finale, parce qu'effectivement, le modèle est assez complexe, mais juste pour avoir une idée de la représentation en termes de couches, alors je ne te demande pas évidemment de préciser l'ensemble des couches, ce serait beaucoup trop long, mais je veux dire, quelle est la taille par rapport à, je ne sais pas si tu as un point de comparaison par rapport à un modèle de l'état de l'art, ou alors, ou tout simplement même citer le nombre de couches, etc. Tu vois l'idée?
Yes. So the question is, what's the size of the model? How many layers are in the model? To be frankly honest, I don't exactly recall how much layers we have exactly in the model. I can give you another information, which is the size of the weight file, which actually kind of, can be very representative of the size of the model. So the size is around 2 MB, which is not a lot at all. So if you compare that to, VGG models, or like maybe other models like that can be several hundreds of megabytes or gigabytes. In this case, the size of the model is not very very big. It's actually small. It's only 2 MB. The only thing that is actually is going to impact the inference time, even though, because basically in deep learning that the very simple logic is to say the more the size of the model is big, the more the inference time will be. In this case, we said that the size of the model is very small, but the inference could be a little bit long. The thing is that the step that takes the more time is going to be the recursions. 3 LSTMs, basically what they do is that they can't be parallelized. What you need to do is that you need actually to make them, the computation step by step. And because it's actually step by step, because it's basically dependency calculus, you need to wait for the steps to actually be done in order to actually make the next step in the inference. So this is why the inference could actually can take some time.
Ah oui, ça va mieux si je remets mon micro. Alors, est-ce que quelqu'un a une dernière question? Ce sera vraiment la dernière question. On va essayer de ne pas trop déborder. Là, on a pris juste 1 heure, pile poil. Une dernière question arrive dans le chat. Do you envision, I don't know what envision mean. Do you envision
Yeah, do you intend using transformer?
Okay, transformer-based approach.
Yeah, so
okay,
basically this is very, we don't use any transformers for the moment in the model. And this is because of the very simple reason that we don't think that using transformers would actually leverage, higher performance today, because we don't have that many samples. We only have 500 pages. And so it's totally possible that transformers would actually be a game changer in the future, but we want first to have more data to be sure that the current, approach is actually very good or not. We are actually we think that if we have more data, we will have way more performance. And at that point, if we think that we need more performance, then at that point we can actually use transformers in the inside the NodeVec, for example, subsystem. The thing is that it's only a matter of what comes before what in terms of prioritization in order to do the things. That's it.
Ok, parfait. Alors, Slim, je tiens à te remercier pour ce talk. Je ne sais pas si... Alors, n'hésite pas, si de toute façon, après à revenir vers moi, si tu veux partager des liens, etc., que de toute façon, je pourrais transmettre à notre audience.
Bien sûr.
Alors, en ce qui me concerne, je le redis, de toute façon, le meet-up était filmé, c'était assez dense, c'était technique. Donc, du coup, vous pourrez, avec beaucoup d'intérêt, retourner sur la chaîne YouTube de façon à pouvoir regarder à votre rythme toutes les informations que Slim vient de nous partager. Voilà. Alors, je vous remercie tous pour voilà, cette réunion. En ce qui concerne la prochaine, elle aura lieu jeudi 7. Des consultants de compte maîtrise seront avec nous et ils vont nous parler de méthodes qui nous permettront en fait en quelque sorte d'adapter les séries, l'information du Covid de façon à pouvoir les traiter dans un cadre de deep learning. Voilà. Le Covid a beaucoup impacté les séries temporelles, ce qui crée des événements aberrants. Il faut pouvoir en quelque sorte traiter cette aberration, cette anomalie, de façon à pouvoir l'analyser par ailleurs dans des modèles de deep learning. Voilà, ça ce sera jeudi. En tout cas, nous, en ce qui nous concerne, je te remercie Slim pour
Merci à
donc
toi.
nouveau ce talk. Et je vous dis pour les autres, tous ceux qui sont encore présents, et d'ailleurs merci pour votre participation encore. Donc je vous dis à jeudi prochain, dans 2 jours. Merci, à bientôt. Merci à tous,
Merci, au
au
revoir.
revoir.
Merci. Au revoir.
Ah, salut Jacqueline, ça va?
Salut Franck, merci Slim. Elle est déjà partie.
Ah zut, ouais, pas grave. Ok, alors,
Il y
ouais,
a
je
encore
lui
du monde en ligne.
je lui transmettrai. Alors,